Hello everyone, this is Robert. So over the years, I've found myself needing to test the layer adhesion strength of various filaments and different types of printing parameters. So I think it's finally time that I make my own filament tensile strength tester. You've probably seen a lot of other YouTubers kind of making stuff like this, and I always like to be pretty late to the party, so I think it's time that I make my own. But I want to approach this a little bit differently by making it really simple, really cheap, and something that once you get all the parts 3D printed, you can throw it together in an hour. I see a lot of these other ones out there that are fantastic, look really cool, but in my mind, they're a little bit overly complicated for what I'm trying to do. So let's go ahead and make our own mini tensile strength tester. So if you've been on YouTube and watched 3D printing videos any amount, you're probably pretty familiar with what this is. Basically, you take a test part like this, you load it into a machine, hit go, it pulls it apart, it measures the amount of force it takes to pull that apart, and you can print these in the horizontal orientation or the vertical orientation, and that will give you a good idea of the difference in tensile strength between the layers or the filament itself. And this is kind of just useful for a few different little projects that I'm working on right now, and especially for the combat robot world, we kind of ultimately want the maximum layer adhesion and the maximum strength because other bots are trying to rip you apart. So why make my own? Well, I wanted something a little bit simpler. A lot of the stuff out there is just kind of a little bit more complicated than I'm looking to do. And of course, making this video and doing this whole thing and putting this up on printables is more work than if I just copied someone else's design, but I don't know, it keeps me off drugs. So a lot of the other designs are actually kind of using a gantry type system, very similar to like what a hydraulic press would be. So you basically have two motors on either side. They're usually stepper motors, which I find interesting, and they, just kind of pull some things apart. I'm going to kind of simplify all of this because all I really care about is consistently breaking these things in half. So I think I have some ideas to make this a lot simpler, and I'm not really convinced that stepper motors are the right way to go. I think I can accomplish this a lot simpler with a lot less electronics and a smaller bill of materials. To make these projects a little bit fun for myself, I always like to approach these things as design challenges. So here is the challenge for myself for this project. All of the components should be readily available off the shelf, very easy to get, so I'm just going to have Amazon links for everything. Nothing custom, nothing crazy other than the 3D printed components. Minimal hardware. A lot of these designs have a lot of hardware. You gotta make multiple trips to the hardware store. I wanna have minimal fasteners and no custom hardware whatsoever. Third, no electronics. I want this to be completely devoid of any electronics, programming, anything like that. So really simple, just put in power and go. And then lastly, this is the big one. This is the biggest challenge of all. Everything 3D printed is going to be just standard PLA. And this is going to be a bit of a trick because there's going to be a lot of forces involved here. So I'm not exactly sure how I'm going to accomplish that, but I don't want people to go out and have to buy exotic filament, use ABS, ASA. So everything's going to be just standard, basic, cheapest, bargain bin PLA for everything. So let's see what we can figure out. So there are a lot of different aspects to this project. So I'm going to start with the structure. Extruded aluminum is always a great first step if you're looking to build something that's relatively large, that has a structure. It gives you a lot of attachment points. It's easy to get. It's a known value. And when you're done with this project, you can take everything off and then reuse this for some other application. And I'm going to try and make this whole design so it uses an off-the-shelf extrusion that you can just buy online so you don't have to cut or modify anything. So let's start with aluminum extrusion for the structure. So next, we need to measure the force that it takes to break each one of these test samples. So I'm just going to keep it simple and use a little luggage scale. A lot of the other projects use like a load cell, and then you have a reader for the load cell and all that good stuff. And yeah, you can log it into a computer, but I'm just kind of looking for the max strength that it takes to break one of these apart. So this little luggage scale actually works well. It does have a load cell in the base, and you can set it for a peak hold. So you pull on this, it will register that peak value, and I think this will work out just fine. These are also really, really cheap, and as I mentioned, I'm going to try and make this whole thing for about under $100, hopefully. So I think something like this will work fine. We'll just have to kind of figure out a way to adapt into it. We have a scale for measuring the load. We have our test sample that sits here. It's all going to fit on this nice aluminum structure, but now we need a way to consistently pull against this sample and break it. I was originally thinking of just kind of some hand crank over here, but that force isn't going to be consistent. It's not going to be repeatable, and there's going to be a problem with that. So the obvious solution is to just kind of have a motor down here, maybe add in some kind of screw rod so that we can kind of pull against that carriage. The problem with this is good quality motors are relatively expensive. This one with a planetary gearbox is about $40, so that kind of kills the budget. That's 40% of the budget right there. The other problem is that we have to now couple this with this. We could probably make a 3D printed coupler, but then we're going to have to support it. So now we're going to throw in some bearings to support it. We're going to need something to kind of interface with this for the carriage. That's all doable. The other problem that we have is that DC motors are not really repeatable. So if we want to reset this so that we can put this test sample back in, a DC motor won't really allow us to do that. So we're going to have to program in or make some sort of end stop, maybe a limit switch, something like that. What does all of this? Well, we can get rid of this, and we can just use a linear actuator instead. A linear actuator does all of this. It has end stops. It's going to stop when the plunger goes all the way in. It's going to stop when the plunger goes all the way out. And we can very simply control it with just 2 wires. It also comes with its own mounting hardware. It has a pretty decent load rating. This one I found on Amazon will do about 200 pounds, so they say, and they move relatively slowly. So I think this will be a good solution. So after a couple hours of mashing the keyboard, yelling at the screen, and clicking the mouse a few times, I came up with some parts for this design. And as I stated previously, I'm just using standard PLA. This is very inexpensive Hatchbox matte PLA, and matte PLAs are actually a little bit weaker than standard PLA. So this will be a good test as to how much of this is the design and how much of this is the actual filament. For slicing, I changed the settings a little bit. I'm just using the standard 0.2 millimeter settings in Prusa Slicer, but I'm increasing the walls to 5, and I'm also using 5 top and bottom layers as well, and I'm using 30% gyroid infill. In regards to the infill, I kind of find that there's diminishing returns once you start going above 30%. Anything above there, you might want to pick a different filament or just kind of change the design, because really I feel that anything beyond 30% just starts to get kind of excessive, and you're really worrying more about the layer adhesion at that point, and that's exactly what we're trying to overcome here because of the orientation of all these parts. The only way that these parts can be printed out of PLA and still survive the forces involved is because of part orientation. So when you see this go together, you will see that I'm only putting strain or stress or load against the parts with the layers. I'm never pulling against the layers because that is going to create some layer separation. So I made sure that when I designed all of this, I am using the parts in the proper orientation that is the absolute strongest for the material and for how I'm printing them. So once I get all of the standard parts printed, I can then start printing some of the optional parts. There's just a couple like little end caps and feet and just some decorative components just to make the whole thing look a little bit better. These are completely optional, and I have everything on printables, so you can kind of check that out, see the notes, and see which ones you need to print, which ones you don't need to print, all that good stuff. So now that we have all the parts, we can start putting things together. I went ahead and put the pins in this piece as well as this piece. These are what's actually the things that are pulling apart the test samples. I just used my arbor press to press these in place, but you could do this any way you want, just a hammer, or maybe even just kind of press it against your workbench. And these are very standard 5mm dowel pins. These are the same things that you can find at the hardware store. They're used for shelving and stuff like that. So these are really easy to get. So yeah, let's go ahead and put the rest of it together. The assembly of this whole thing is really straightforward. I think it only took start to finish maybe about 15 minutes. It's pretty easy. I'm going to start with the linear actuator side. It includes these metal mounts, so I'm using one of them for one end. You just kind of put the pin through, put the cotter pin on, and I'm using a couple screws to secure it. Now, these fender washers, the big flat washers, are not absolutely necessary, but I did have some on hand, so I figured I might as well use them because it does kind of help spread the load across these larger faces. And I do have a link down below for a fender washer kit. Sometimes it's kind of nice to have something like this on hand because, I don't know, fender washers are kind of hard to find, at least for me, at the local hardware store, so it's just kind of nice to have them on hand. Once you get the linear actuator installed at the very end of the rail, we can install the carrier pieces on the other end. These just kind of slide in, and you definitely have to make sure that this and the following piece slide in freely. These need to be free moving. You don't want these binding at all. So if you do have some issues with binding, you might want to just sand down those inner surfaces a little bit, but they are sized with a little bit of spacing, so they should be totally fine. This actually connects with just the other pin that's meant for the other end of the linear actuator. If your hole isn't aligned, the end of the plunger kind of rotates. It basically unscrews a little bit. So you just unscrew it to where it's vertical, shove in that pin, those pieces are together. The next step is to start installing the brackets for the luggage scale. There's 3 screws per side, and I am once again using the fender washers just to spread out that load, because you really got to tighten these down. But don't tighten them just yet. Just kind of get everything loosely assembled for now. For the luggage scale, we need to make a couple of small modifications. We're going to take this top bar off, and that's really easy. You can just undo these screws, and then take that off. And for the hanger here at the bottom, you're just going to want to cut off that little link, so that ends up looking something like this. So we just kind of have it bare, and then we have the hook separate. The hook is just going to kind of go in like that, and we're going to use it like that instead. I also added a piece of tape on the back of mine because this battery compartment will kind of pop off. There's a lot of violent forces when this thing actually breaks. So yeah, just make sure you kind of tape that in place, or else you're going to be having to take this whole thing apart. There's a bit of an order of operations for the luggage scale side of things, and as you can see, I really didn't follow it. You kind of need to put the luggage scale inside those 2 supporting brackets, put the hook inside, and make sure that you put the screw inside that little carrier block, and you need to make sure it goes through that hook because, yeah, it doesn't go on afterwards. So screw that down in. It should be just kind of a self-tapping size. I made it so that it's relatively easy just to kind of screw it in by hand or with a little screwdriver. And then once all that's in place, you can arrange the scale inside the brackets, but don't tighten anything down yet because we need to adjust the distance between everything. So just kind of get everything loosely in place for right now. Once you get that all together, you can slide on the feet and then slide on the housing for the switch. The feet kind of go anywhere you want them to go. They don't really fix in place, but they're just kind of there to keep it from tipping over. And then the switch enclosure fits on the one side of the linear actuator, and it kind of butts up to the very end of the rail. So we've got this thing almost together. I've got the optional feet at the bottom, as you can see. This is still loose over here because we need to kind of set this distance, and that is dependent on the travel of the linear actuator. So we need to actually turn this thing on and, extend its travel so that we can set this distance and then tighten everything down over here. I have this switch in the description. This is just a simple 2-pull, 2-throw momentary switch, and it's wired such that when you put power into it over here and connect this into the linear actuator, it will go one way and then go the other way. And it's just simply reversing the polarity, but these switches are really common. I have a link for one on Amazon, and that is going to fit inside of here. And then I'm also using a barrel jack. As much as I don't want there to be any soldering or any electronics in this project, I couldn't really avoid this. In theory, you could just plug this into a power supply and then reverse it. But the switch makes things a little bit easier. So I'm going to get the switch all wired up, then we can set the linear actuator, and then we can tighten everything down. There's a hole in this little enclosure for the wire, the cable for the linear actuator to come into. I'm just kind of cutting it down to length because it is way too long. And I also included this neat little feature for where the wire comes in. You can just run a zip tie through this little channel and then secure everything in place as a little bit of strain relief. Now, I don't believe in the idea of a traditional God, but I do believe in Wago lever lock connectors. I absolutely love these things, and for an application like this, I think they're absolutely perfect. I'm just using a couple of those to connect the ends of the linear actuator to the ends of the switch, and then I'm gonna solder in a barrel jack off camera so that the power can come into the opposite side of this little enclosure. Getting the little nut for the barrel connector on here is just a real pain, but it's not too bad, and everything fits in here nice and tidy. Now, a little bit of a note here. If you get the polarity of your switch backwards, obviously the linear actuator is going to move the wrong way from what you expect from the switch. It's just a simple matter of flipping the cables on the Wago connectors. You could even just rotate the switch around too. Either one of those will work. Once all that is going the right direction and everything looks good, we can put on the lid for this housing. It once again just uses these self-tapping screws. I think this is sized for a 1032 or a 1024, or I think an M5 would work just fine as well. And the sizing is such that you can just screw it in, no problem. Just don't go too crazy with it because you will strip it out. So there you go, it's almost fully together. Now we just kind of need to set this distance. I'm using these little test samples I created that are about that distance apart from each other. So what we're going to do is we're going to extend the linear actuator to the end of its travel till it stops. And then for this, we're just going to kind of set it in there, undo these fasteners. Where's that? Undo these, slide it in place, and then that's pretty much all there is to it. Nothing too crazy. Yeah, so you want to have it, just a little bit loose. You don't want it to obviously start out tight because you want to be able to remove and put that back really easily. So everything is all tightened up and ready to go. One of the notes about tightening these bolts on both sides is you need to have these really tight as well as the two in the back for the linear actuator. If you don't get these tight, the whole thing will just kind of pull in together. This has a lot more force than you might expect. So get these tight. If you start to hear the plastic cracking, maybe that's a little bit too tight. Another note about the actual scale is if we turn it on, you can see this hold button. We can kind of go through this menu. What you want to have it do is this is a max hold function. So when I pull it, it should actually stay. And you can see right now it's resetting back to 0. So we'll go max hold, and then it will stay. Now we can 0 it. Now we're ready to throw some samples into it. So now everything is ready to go. I have this plugged into a power supply on that side. This is just plugged into my bench power supply that I have kind of here on all my workbenches. 12 volts, I think they have the current limited to like 10 amps, so this should be plenty. I think it only uses like 30 to 50 watts. And then I have my little test samples. These are just I think it's a Polymaker PLA, just a relatively cheap filament, and this is printed flat. I still got to kind of play with the geometry of these because I'm not quite maxing this out, so I got to maybe make this thicker, but this has about a 10 millimeter, square millimeter cross section. So All you have to do is load this in, hit the button, snaps it, moves it back. That was 38.5 kilograms. Load another. Really, really simple. 38.5 once again. Let's do another one. I could do this all day. 37.7. So yeah, everything works as it should. I just got to do a little bit more calibrating on these because I kind of want a little bit more force out of this. But I think this will do what I want. So let's talk about the next steps. So overall, I think for my purposes, this is going to work just fine. I initially wanted to create something like this because I want to test the relative layer adhesion strength between different filaments, also between different printers, different temperatures, and also between different print speeds. There's a lot of information out there that high-speed printing can produce actually weaker parts, and I have a little bit of anecdotal evidence from this, but I want something a little bit more scientific, and this is a little bit of a step up. This is by no means the nicest tensile tester out there, and it will kind of hit a wall in terms of scientific accuracy very quickly, but this is also something that you can download and build in an afternoon. It is really cheap and quick to build. So hopefully this will work out for what I'm trying to do, and if not, I'll make another one and update the design somehow. I need to kind of figure out a better way to size these because we're really not using the max potential of this. This supposedly can do about 200 pounds. My guess is probably only about 100, 150, and this tops out about 100, 110 pounds. So, I need to kind of size these up a little bit, but different filaments are going to be different. So I'll probably have a lot of different sizes of these depending on the type of filament that you use. But ultimately, I have some ideas on how to dramatically increase the layer adhesion strength, which will be really good for the combat robot people. I'm kind of toying with a new design. I'm also kind of looking at drain damage over there, trying to kind of finish that off for a competition. So, this was kind of the reason for doing all of it. The last thing I want to talk about is I built this design with these two pieces being sacrificial. So this piece and this piece is basically where all the load kind of comes in. So you might want to print an extra of this and an extra of that. These will be the wear pieces. And if you really go crazy with it, these two might break. So you can always maybe print these out of something like ABS or something stronger, but I wanted to keep it away from exotic filaments. So hopefully you guys find this helpful. It was kind of a fun design to put together. It kind of went off the rails. You can kind of see in the design where I just kind of gave up and I'm just like, I just want this to be done. But overall, it does function. It's cheap to build. You can make it out of standard PLA, so I'm happy with all the design objectives, and it is fun to load in a part and snap it. So that's pretty cool. Thanks for watching. See you in the next video.